Welcome to day 2 or recording number 2 for physics. Today we're going to be covering the period of a spring mass system as well as the period of a simple pendulum, and we'll talk about the simple pendulum a little bit in depth. But let's go ahead and get started. So we'll jump over to this. We'll take some notes on it. So the first thing we're going to do is the period. We talked a little bit, and frequency. We talked a little bit about this in the meeting, but all of you weren't in the meeting, so I want to make sure that I'm perfectly clear of a. Okay, so first of all, let's talk about we talked a little bit about this, but back in circular motion. So this is kind of like, remember what we did in circular motion when we had the bat and the pig and everything. And so we talked about the velocity, and the velocity of this was equal to 2 pi r. Why 2 pi r? That's the circumference of the circle. So it was the distance. It was the distance around the circle divided by the period, because that was the time it took to get around that circle. So this is just another formula. Basically says distance over time. Okay, so that's just another formula. Now, in simple harmonic motion, we can actually take this idea, because the motion is back and forth and can be mapped out very similar to this. But instead of 2 pi r to find the total distance, we actually use, so this is for a spring, we actually have v sub 0. This is the max speed, is equal to 2 pi times the amplitude over the period of the motion. Remember, the motion would be all the way, like if we had a spring here, the motion would be all the way out, all the way back into where it started. And we can solve this for period, and we end up getting t equal to 2 pi a over v sub 0. However, this formula is not easy, because you have to find v sub 0. But we can do a little bit of work and actually make this formula way more simple, where we don't have to find v sub 0, because v sub 0 can be very tedious to find. So if we recall that the E total, the energy in the system, is 1/2 Ka squared. That's the potential energy at the equilibrium. I'm sorry, at the amplitude. We also have the formula E total equals, again, energy total is equal to 1/2 mv squared. That's v sub 0 squared for the speed at equilibrium. This is the maximum speed, right? So notice we can set these two things equal to each other. So that's what I'm going to do. All right, and now notice what I have here. I have an a on this side, of v sub 0 here. Notice what I have right here, an a over v sub 0. So what I'm really trying to do here is get these two things to basically be able to get a substitution here. So let's try that. So first of all, notice the 1/2s just cancel. And so I'm going to move, we want the a on top, so I'm going to divide by k on both sides. So then I get a squared equal to m over k v sub 0 squared. Now I'm going to divide both sides by v sub 0 squared. Okay. And we end up getting a squared over v sub 0 squared equals m over k. Notice these are both perfect square. Whoops, sorry. These are both perfect squares, so I can just square root. All right. And we're only really interested in the positive answer, so I'm going to just leave it as the positive. But this ends up giving you a over v sub 0 equals the square root of m over k. Why is this a good thing? Because now I have this relationship of a over v sub 0, which is exactly what I had up here, a over v sub 0. So all I got to do is take this substitution. I'm going to make this substitution and put it into that period formula. And this makes life a lot easier. Why does it make it a lot easier? Well, because here I only need the mass and the spring constant, and these are two things that are way easier to find than the max speed. Because to find the max speed, we had to find the potential energy, and then you plug it into this formula and solve for v sub 0 there. Okay, so it's a way less of a process. So what is our formula? T equals 2 pi times the square root of m over k. I know we got a square root in there, and that can be scary, but don't be afraid of that. Okay, so that's our first formula. For frequency, it's really just 1 over all of this. And that ends up giving you, really, it's just 1 all over that. So you could always just find the period and take the reciprocal of it. But for the sake of being complete, it ends up being 1 over 2 pi times the square root of k over m. Notice everything has just basically been reciprocated. Okay, and that, so it's nothing and nothing too fancy. So these are your 2 formulas. Okay, for that. Let's do a quick example. I'm going to say, if you need to pause that, because those are the important formulas. Write those, make sure you have those, write those down or something. All right, so we're going to do a quick example, just kind of using that idea. Example 1, we'll talk about a small insect. Let's call it 0.30 grams. A small insect, 0.03 grams. Notice it's grams. Okay. Where is it? It's caught in a spider web. It is caught in a spider web. I should say spider's web. All right, and let's just say, what do I want for numbers? The web vibrates. The web vibrates with a frequency of, let's call it 15 hertz. So let's find, make sure I'm going to space it, find, okay. And what about, and then find part B, this is A, we'll call that A, and B will be like, let's say, I don't know, find the frequency if the insect was 0.10 grams. Okay, so notice we're just finding, the first thing we're going to do is find K. And notice we're given the frequency and a mass. So if I go back over here, if I go back up here, notice the formula I just gave you involves those 3 variables: frequency, K, and mass. So we only have to use this one formula to find that K. We're going to substitute in the frequency. It's given to us in hertz. It's given to us in hertz. We're given the mass of the bug. We're going to plug that one in. And the rest of it is just algebra. So we're going to plug in the 15, plug in the 0.30 grams, then we're going to find K. Notice that we're dealing with very small numbers here, so I wouldn't expect to have a big K. But let's try it. So first of all, frequency 15 equals 1 over 2 pi times the square root of our K, which is what we're trying to solve for, over our M, which is 0.3 grams. We should probably convert that. Let's make sure we convert that to 0.000. One more 0. 1. 3 zeros. Okay, kgs. I think that's right. Yeah, that makes sense. Okay, so that's in kgs now. So make sure we're using this number and not that number. So how do I solve this thing? Well, the first thing I probably do is multiply both sides by 2 pi. Right? Get rid of this guy. Get rid of that guy. And so over here, we're going to have 2 pi times 15 equals the square root of K over 0.0003. Now, to get rid of a square root, I'm going to square both sides. Square, square. All right. And so I square both sides, and I end up getting this guy squared equals K over 0.03. So final step will be to multiply by 0.0003, multiply by 0.0003. So let's put that in our calculator. All right, and see what we get here for K. All right. So I'm just going to do it all in one step. I've done all the math work here. I need to square this. I can put that in parentheses, square it, multiply by that. Do that all in one step with my Handy dandy calculator. All right, let's try 0.0003 times parentheses 2 times second pi times 15 end parentheses squared. There it is. So doing it all in one step. Let's take a look. And we end up getting a small k, but not anything too crazy. 2 point, I don't know, let's go 66, 2.66. So k equals 2.66. So now I know k, that's newtons per meter. All right. And now it says find the new frequency if the insect was only 0.1 grams. So again, recall that formula from before. It was F equals 1 over 2 pi times the square root of K over M. Oh, sorry, guys. Let me move up. There you go. There you are. All right, that's a pi, by the way. That's a pi. Just terribly drawn. All right, so we're going to substitute our numbers in. We know K. We know the new mass. We're looking for F. This is the only formula we have to use. So equal to 1 over 2 pi times the square root of K, which is 2.66 all over 0. Notice 0, 0, 0, 1. Now we got to change that to kilograms, right? That's kgs now. All right, let's throw it in our calculator and find out what our answer is. Again, doing it all in one step, multiplication and division. So we should be able to do pretty fine with this. 1 divided by 2, whoops, I meant to move that parentheses. 1 divided by parentheses 2 times second pi. I don't know if I do them right next to each other if they work, so I just do it like that. Times the square root of 2.66 divided by 0.0001. And we get a frequency. Now, smaller mass. Smaller mass doesn't mean bigger frequency. Let's make sure. Does that make sense? If you're dividing by a smaller number, do you get a bigger number? Absolutely. So it makes sense that our frequency went up, right? It makes sense that our frequency went up when we're dealing with a smaller mass. Okay. So we have a frequency at 25, really close to 26. I would just call that 26 hertz and pretty much be done with it. So let's just do that because if I was rounding it, it would be 26 hertz. So F equal to 26 hertz. All right, and that's dealing with the frequency. I noticed I didn't really deal with period in this problem, but similar idea using that formula. So I wanted you guys to see an example solved out. Sorry for this. It looks very messy when I look at it. But that's the idea, okay? I'm going to move on to simple pendulums, okay, which is a similar process. And so we'll talk about a lot of similar things. But how much time have I been on here? Let's I don't want to kill your whole day watching this video. It doesn't really tell me how long. Hopefully I haven't been doing this for too long. I'll probably just cover the frequency of a simple pendulum. I don't know if I'll have time. We'll give it a shot. Whatever. This one might be a long video. Sorry, guys. But I want you guys to be able to do it. So, simple pendulum. Simple pendulum. All right. So what are we talking about? Simple pendulum. Actually, what I'd rather than me draw it, I'd rather show you guys. All right, this is a simple pendulum. All right, so I'm gonna do a couple things. Let's along. I like the length. Earth, that's good. Mass, let's jack it up. Length, let's go all the way. Okay, so notice I'm giving it an angle here. I'm gonna give it 5 degrees. Okay, because with simple pendulums, we're always dealing with small, angles here. We'll never really get bigger than 15 or 20 degrees. Sometimes they give it bigger and they're just like, assume simple harmonic motion. But notice this thing just continually goes back and forth. All right, and over here, let me jack up the energy. All right, so here we're dealing with that rotation of kinetic energy and potential energy. Okay, so we're just giving it, if I stop this and I move it over here, look at all the energy, right? It's all potential. All right, now what type of potential energy am I giving it? Well, not elastic, certainly. So it must be PEG, or potential gravitational energy. So I'm displacing, I'm moving it upwards, okay, a certain height, and I'm introducing energy into the system. And when I let it go, again, here's the equilibrium line right here, this dashed line. And so what do we see here when it passes there? All the energy is kinetic. So it's the same idea of when it passes through equilibrium. Okay, where's the force the most? Force is the most right here when gravity's trying to pull it back down. All right, and then right there, where's the speed the fastest? Right when it's passing the equilibrium. So notice those relationships are still the same. And so those formulas still work. Okay, so all of this is still good. That's why we can deal with a simple pendulum. That's why we bring it up here. It's just a different type of a simple harmonic oscillator. So it's still simple harmonic motion though, okay? We can try to time one period with this guy. So again, I'd probably try to, I'm gonna try to do it from there. Okay, so I'll probably do ready, set, go. And right there. Okay, so right about 2 seconds when I have all about this. And we could do the math to figure out if that was right, but only after I show you the formula. So notice I have length 1 meter. I have a mass of 1.5 kilograms. I don't know why it says only 1, but 1.5 kilograms. And then I have a gravity set to Earth. So let's see how close I was timing this and see how close I was. Let's try it one more time because I want to make sure I get a good answer. Ready, set, and go. All right. Oh, I forgot to undo this. Ready, set. Okay, so really close to 2 seconds. So very close to 2 seconds. I'm getting 2.04, 2.01. So we'll see if that's pretty dang close to what it should be. Maybe that's the example we'll give. So stop it. I'm going to jump back over to here. This is a simple pendulum. Okay, very simple. A mass hanging on a string, technically a massless string. We displacement a certain degree. Our displacement is a certain degree. Okay, and we're able to calculate how much energy we put into that system based on that stuff. So let's get working. Let's write some of this stuff down. So simple pendulum. Okay. So first of all, let's go over a couple of things. All right. So I'm setting up my pendulum here. Let's just throw a ball on the end. This is my equilibrium line. All right. And let's talk about the different things going on here. We got L as the length of the string there. Over here, when I was looking at this one, I had given it a length of 1 meter. Okay, I gave that string a length of 1 meter. We saw that right here up in this corner. Okay, so but here that's that L. Okay, so when I'm talking about that L, it's just the length of the string there. And so let's talk about, we have a mass over here, okay, just like it was on the spring. And let's talk about the restoring force. So in a spring, we called the restoring force, can you see that? Yeah. In a spring, the restoring force was F equal to KX. And that's where we all started. So we got to start kind of in the same place. So where's this restoring force happening? Well, when we swing this up, right, when we swing this thing up like this, okay, the restoring force is, again, notice this is kind of an arc of a circle. If I was to rotate this all the way around, I would have a circle. And so the restoring force always acts tangent to that motion. And that makes it easy because tangent to a circle gives us a 90 degree. All right, so this is the restoring force. I'm going to call it FR for restoring force. Notice the different forces we have. We have this force right here along this line. This would be the tension in the string, FT for tension. And then what acts straight down? Okay, what is acting straight down? Or in this case, let me make sure I'm drawing a triangle right. Just like everybody, we always have fun drawing triangles, right? Okay, I think so. Yep. Yeah, Okay, what's acting straight down? So notice basically what I've done is I've taken this side. This is mg, right? And I've just moved it over. It's a parallel line. So I'm just redrawing that triangle with the hypotenuse here. And notice the hypotenuse is straight down. We have that 90 right here. And so this is also mg. I just redrawn this line up here, but really you could draw it like this. And then you could do all kinds of stuff here, creating that parallelogram here. Notice parallel, so the tension could also be found here. All right. But really what we're interested in is that restoring force. Okay. So if I was using that restoring force, again, here's theta. Notice similar triangles there. So really, we're dealing with the opposite side for the restoring force. So Fr, the restoring force in a pendulum. So this is the same idea here. It's that same idea there. This would be equal to mg times sine of theta. Okay, why is it sine of theta? Well, because this is the opposite side, right? So if I was trying to deal with that, I would say something like the sine of the theta is equal to opposite, which is Fr, times the hypotenuse, which is mg, right? And then we solve that for Fr, and we end up multiplying both sides by mg, so you get mg sine theta. Recall that we had a negative up here, and that idea is also used here, where we can throw a negative onto this to understand that it's always acting against the motion. You can leave, I like to leave it off because I think introducing negatives always can be confusing. But this is where we start. All right, right there. All right, that's where we start. And that really allows us to talk about, and we're going to introduce this other idea that what's the best way to think about this? So, I forgot to talk about the displacement. So first of all, one thing I also want to talk about is, before I get to this next thing, is when we're talking about the energy we're introducing, how far did I move this? What is the real displacement of this? And so that idea of moving this guy, and well, it started here, right? And I've moved it to here. Well, how do I get there? Right? How do I get there? So what ends up happening here is I can form another right triangle and figure out the displacement, right? Really, the displacement is this x. All I'm doing is displacing it x amount up. I'm just displacing it x amount up, okay? So what I really want to do is figure out what was the change in the height here. All right, this L is the same here as the same here. And so really I'm just looking for this difference here. And that ends up being, okay, it ends up being, x equal to L times the sine of theta. Okay, you can try the trig out for yourself. I'm asking you to trust me on that x equals the L sine theta. I'm not going to go, it's already messy enough as it is, and I don't really, but we need this idea that displacement, because notice here, we're trying to relate these two. And we're going to be able to do that in just a second here, because we're able to basically understand that we can do a little substitution here. We're going to be able to do a little substitution here, and that's our goal. So notice for a spring, it's F equals Kx. For a simple pendulum, we have mg x equal x, mg sine theta. And so what we can do here, all right, is basically it turns into doing a little bit of substitution and understanding this idea. Please let me know. You can try this in your calculators. 4 theta less than, I don't know, 5 degrees. The sine of theta is pretty much equal to theta. This is a key fact for simple pendulums. What does that mean? Take a look at my calculator real quick. Small angle, sine of 5. Oops. What was I doing? Give me 1 second. Oh, I'm sorry. I needed to do this in radians. That's right. Okay. So for example, for small, so 15, so let's just take 5 degrees for a second. 5 degrees in radians. So we have to convert that into radians. What's that? 5 degrees equals, what's that conversion? 180 over pi? Invert it. Pi over 180. So take a look at this. So if I convert this to radians, so 5 times second pi divided by 180. All right, so if I take the sine of that, so this would be like taking the sine of 5 degrees. Notice that they're almost identical. And what that means is just this relationship. For theta less than 5 degrees, the sine of theta is equal to theta in radians. I'll make that caveat because I didn't say that earlier. Okay? Why is that important? Because now I can eliminate all these signs. And I get x equals L theta. FR equals mg theta. All right? And we can make one more substitution, making our life a heck of a lot easier. Here, I can get theta equals dividing by L, x over L. And then so for down here, FR equals mg times x over L. What did I do? I eliminated the need to do any trigonometry. All right, I eliminated the need to do any trigonometry in that question. All right, and that is why this works very well. Okay, now comparing this, okay, up to here, okay. Notice I want to get these things related. Now I have an x, I had an x. Here, this was a spring constant. This is mg over L is also a constant. So the way we usually write this, let me slide up, is the restoring force is equal to mg over L times x, where this is equal to the spring constant, in this case, the pendulum constant, okay? And now we have a very similar idea, okay? This was newtons per meter. Mg is a force. L is a length. That's a newtons meter. So notice this, it's the same idea. It's the same formula, all right? This is just for a pendulum, and this is for the, this is for a spring. So this is the big formula for today. How does that relate for us? Well, then we can relate it back to, recall that the period for a spring, so notice this is kind of like K. Spring, we had T equal to 2 pi square root of M over K. But we're not dealing with K anymore. So for the pendulum, T equals, now notice this is K, right? If I'm comparing these two formulas, K was just K here, but now I have this mg over L thing. So now all I'm going to do is substitute the mgl into here. Still 2 pi, still times the square root. Still have, if I do a little bit of work here to clean this up, okay, if I'm substituting in mg over L there, the m's cancel. All right, and I'm just left with, and then I could take the reciprocal, and I just end up with L over G. All right, you can do the little bit of algebra because I want to end this pretty fast here for today. All right, because I feel bad. And I'll be available later to talk any about this. And so this is the formula for the period of a pendulum. Taking the reciprocal of everything, very similar to what we did before. F equals 1 over 2 pi, frequency equals 1 over 2 pi times the square root of G over L. Okay, so there's the frequency formula. And that is all I wanted to cover for today. I feel like I've been going on for a really long time. So I'm going to end it. I'll be available for questions and everything later, probably either today or Monday. All right. I appreciate you guys sticking around and letting me drone on for whatever reason. All right. Thanks, guys.